Welcome to Opulenta.ai. I am Opulenta. Today I want to talk about software development. Please feel free to pause the video and look up any words that you don't understand before continuing. Let's talk about data operators in Python. Welcome, everyone, to today's lecture on data operators. We are going to get into more detail and provide some discussion and examples. Lecture: Introduction to Data, Python Operators, and Processing Data. Welcome, students. Today, we will delve into the fascinating world of data, explore the essential Python operators, and understand how data is processed. Let's begin. Understanding data. Data is at the heart of computing. It refers to quantities, characters, or symbols on which computer operations are performed. Data can be stored and transmitted as electrical signals and recorded on various media. Think of data as the raw material that computers work with to perform tasks. It can be anything from numbers to text, and even information gathered from sensors like heartbeats or steps taken. The binary system. Computers process data using a binary system, which represents information using ones and zeros. This binary system was developed by George Boole, an English mathematician. It allows computers to interpret the 1 and 0 as on and off signals for the computer's internal switches. Variables and data types. In programming, we use variables to store and manipulate data. Python supports different data types, including integers, represent whole numbers. They are typically 16 bits long, allowing values from -32,767 to 32,767. Floats represent decimal numbers. They can store larger numbers with decimal places. Strings represent text or characters. They are enclosed in quotation marks. Python operators. Python provides several types of operators for manipulating data. 1. Arithmetic operators perform mathematical calculations, such as addition, subtraction, multiplication, and division. 2. Relation operators compare values and determine their relationship, like greater than, less than, equal to, etc. 3. Assignment operators assign values to variables. 4. Logical operators combine conditions and determine the logical outcome, such as and, or, and not. 5. Membership operators check if a value exists in a sequence or collection. 6. Identity operators compare the identity of objects. 7. Bitwise operators perform operations at the binary level. 8. Processing data. In addition to understanding data and operators, we need to process data effectively. This involves 9. File processing, reading and writing data to files. 10. String processing, manipulating and analyzing text data using various string operations. 11. Regular expressions, powerful tools for pattern matching and text manipulation. Compilers vs. Interpreters. Programming languages can be compiled or interpreted. Compiled languages, like C or C++, convert source code into machine code before execution. Interpreted languages, like Python, translate code at runtime. Interpreted languages offer flexibility, but compiled languages tend to be faster. Importance of understanding limits. It's crucial to understand the limits of data representation in computers. For example, integer values have a limited range, and exceeding these limits can result in overflow errors. These errors can lead to severe consequences, as seen in incidents like the Ariane 5 disaster and the Boeing aircraft crashes. Awareness of computer limits helps prevent such issues. Let's unpack some examples in more detail. Ariane 5 disaster. On June 4, 1996, the European Space Agency, ESA, launched the Ariane 5 rocket for the first time. However, shortly after liftoff, the rocket veered off course, broke apart, and exploded, resulting in a catastrophic failure. The cause of this disaster was a coding bug in the rocket's software. The bug occurred when converting velocity data from a 64-bit floating point format to a 16-bit integer format. The velocity reading exceeded the maximum value that could be represented by a 16-bit integer, causing an integer overflow. The overflow error was not handled properly, and erroneous data was sent to the main flight computer. As a result, the flight computer misinterpreted the data and made incorrect adjustments to the rocket's trajectory, leading to its destruction. Boeing 787 aircraft crashes. There have been concerns that overflow errors might have played a role in the crashes of Boeing 787 aircraft. The navigation computer of the Boeing 787 had to be restarted every 248 days, which is the maximum value that can be stored in a 32-bit signed integer, 2,147,483,647. If the navigation system was left on for longer than 248 days, the computer would encounter overflow errors, resulting in incorrect values and potential system crashes. While the exact cause of the crashes is still under investigation, overflow errors have been considered as a possible contributing factor. These examples highlight the importance of understanding the limitations of computer systems, particularly when it comes to representing and processing data. Failure to account for these limitations can have serious consequences, as demonstrated by the Ariane 5 disaster and the potential impact on aircraft safety. It emphasizes the significance of thorough testing, error handling, and awareness of the boundaries within which computers operate. The big lesson from these examples is the critical importance of software quality, robustness, and thorough testing. It highlights the fact that even seemingly small coding errors or oversights can have disastrous consequences. Here are some key lessons to take away. Proper error handling. Software developers should anticipate and handle errors effectively. In both examples, the failure to handle overflow errors correctly led to catastrophic outcomes. By implementing proper error handling mechanisms, such as validating input data, checking for potential overflow conditions, and gracefully handling unexpected situations, the impact of errors can be minimized or mitigated. Rigorous testing. Comprehensive testing is crucial to identify and address potential issues in software systems. It is essential to thoroughly test software under various scenarios, including boundary cases and edge conditions, to ensure it performs as expected. In both cases, the errors could have been caught through rigorous testing and validation processes. Awareness of system limitations. Understanding the limitations of computer systems, such as data representation constraints and potential pitfalls, is vital. Developers should be aware of the capabilities and vulnerabilities of the platforms they are working with and design their software accordingly. Awareness of limitations helps prevent errors related to data overflow, data loss, or incorrect calculations. Continuous monitoring and improvement. Systems and software should be continuously monitored and improved based on feedback and real-world usage. The Boeing 787 example highlights the importance of periodically restarting systems to avoid potential issues related to integer overflow. By actively monitoring and addressing such issues, system reliability and safety can be improved. Collaboration and knowledge sharing. These examples underscore the importance of collaboration, knowledge sharing, and learning from past mistakes. Sharing information about software failures, conducting thorough investigations, and disseminating the lessons learned can help prevent similar incidents in the future. The software development community can collectively benefit from understanding and addressing the root causes of software failures. Overall, the key lesson is to prioritize software quality, error handling, testing, and continuous improvement throughout the software development lifecycle. By doing so, we can mitigate the risks associated with coding errors, enhance system reliability, and prevent potentially catastrophic consequences. Let's talk about backup systems for a moment and expand our set of examples. The backup system in the case of the loss of NASA's Mars Climate Orbiter mission did not work because it was designed to perform the same unit conversion error as the primary system. The error occurred due to a mismatch of measurement units between the software components responsible for the spacecraft's trajectory calculations. Specifically, the software that provided thruster performance data to the navigation system used the metric unit Newton-seconds, NS, to represent impulse, which is a measure of how much a thruster can change the spacecraft's velocity. However, another software component in the navigation system expected this data to be in English units, specifically pound-seconds, lbfs. As a result of this oversight, the navigation system made incorrect calculations using the thruster data, leading to a discrepancy between the expected trajectory and the actual trajectory of the spacecraft. This discrepancy ultimately caused the Mars Climate Orbiter to approach Mars at too low an altitude, and it likely disintegrated in the Martian atmosphere. The backup system, unfortunately, did not prevent the error because it used the same flawed software logic and unit conversion process as the primary system. When the primary system failed due to the unit mismatch error, the backup system replicated the same error, leading to the same disastrous outcome. This incident highlights the significance of thoroughly testing backup systems independently from the primary systems. A robust backup system should be designed with different code, algorithms, or methodologies to ensure that it can take over seamlessly in case of a failure in the primary system. Additionally, it underscores the importance of proper communication, coordination, and review processes during the development and testing of critical software components to catch and rectify such issues early in the project lifecycle. In the case of the Ariane 5 rocket failure, a simple line of code and the concept of floating point numbers played a significant role. The issue arose due to the reuse of software code from the Ariane 4 rocket in the Ariane 5's Inertial Reference System, IRS. This software component was responsible for measuring the rocket's horizontal velocity, an important parameter for guidance and navigation. The specific line of code that caused the failure was responsible for converting a 64-bit floating point number to a 16-bit signed integer. This conversion was necessary because the Ariane 5's horizontal velocity exceeded the range of a 16-bit integer. However, the floating point number being converted in this particular scenario was larger than what the 16-bit integer could handle, causing an overflow. The overflow error in the conversion resulted in an exception being raised, which was not properly handled in the software. As a result, the software component controlling the IRS shut down, leading to the loss of critical guidance and navigation information. This ultimately triggered the rocket's self-destruction mechanism. Now, to address the question of whether the code was necessary, the answer is yes. The software code was crucial for the operation of the Inertial Reference System, which played a vital role in measuring and maintaining the rocket's intended trajectory. Without the code, the IRS would not have functioned, and the rocket would have lacked the necessary guidance and navigation capabilities. The failure was not due to the code being unnecessary, but rather the oversight in reusing code from the Ariane 4 without adequately considering the differences in the systems. The Ariane 4 and Ariane 5 had different performance characteristics, including higher horizontal velocity for the Ariane 5. However, the reused code was not modified or adapted to account for these differences, leading to the overflow error. The speed of the rocket in reality is not directly related to the coding itself. The code was responsible for interpreting and processing the data related to the rocket's velocity, but it did not determine the physical speed of the rocket. The failure occurred because the code was unable to handle the unexpected values arising from the higher velocity, leading to the loss of critical functionality. This incident emphasizes the importance of thoroughly reviewing and testing software code when it is reused or adapted for new systems. It also highlights the need for careful consideration of system differences and potential edge cases that could arise during the reuse process. Additionally, proper error handling mechanisms should be implemented to ensure that failures in one component do not cascade and affect the overall operation of the system. Conclusion: in this lecture, we covered the fundamentals of data, explored Python operators, and discussed data processing techniques. We also discussed some examples to make it real. Remember, data is the foundation of computing, and understanding how to manipulate and process it is essential for software development. Keep exploring and practicing these concepts to become proficient in Python programming. Thank you for attending this lecture, and I hope you gained valuable insights into data and Python operators. I hope you enjoyed the examples and discussion. Please feel free to have a look at our website and go to the blog section to read more. www.opulenta.ai. Subscribe to our YouTube channel to keep up to date. If you would like any specific help, contact us on result@opulenta.ai. Thank you for watching. Bye.